In this lecture, we'll continue with our metrics of controller system performance. Previous lecture, we looked at sensitivity analysis. In this lecture, we are going to look at tracking and disturbance rejection. Before we go into these two topics, I'd like to look at typical control system configuration. So this is what you will typically encounter. So you have this control system where D is the controller, G is the plant, H is the transfer function for the sensor. If the sensor has no dynamics, then H equal to 1. R is the reference input, WA is the actuator disturbance, WL is the load disturbance, and WS is the sensor disturbance. Because these systems are linear, at least in this class you're only worried about linear systems, we can analyze each of the inputs one at a time and then sum all the results together. So for tracking, you're basically interested in the reference input, and you'll set all the disturbance inputs to 0. And when you do each of the disturbance inputs, you set all other inputs to 0. So for example, if you want to do the disturbance rejection analysis for disturbance through WA, you will set WL equal to 0, WS equal to 0, and the reference input equal to 0. Tracking. And tracking is the ability of the system to perfectly track the reference input. So we are worried about what the steady state error is. Ideally, we'd like to have the steady state error to be 0. Here's an example for tracking. So the dotted line that you see is the reference input. Reference is what you want. The solid line is the output. It is what you get. Now, if the solid line perfectly matched with the reference input, then we would say you have perfect tracking. Now, you do not have perfect tracking. So that's what tracking. So tracking is a measure of this imperfectness, this error. Essentially, steady state error. So let's look at working out tracking. So this is your system here. So since tracking is with respect to the reference input, all the other inputs are 0. Now we have to find what the steady state error is. Therefore we need to know what the error is. That's the error signal here. And if you set all these inputs to 0, you can reduce the system like so. And now we need to find a relationship for error in terms of the reference input and these transfer functions. We do this by brute force, and that is your error signal with respect to the reference R. So let's do an example. Let's say your controller is 1 divided by S, your plant is 1 divided by S plus A, your sensor dynamics is 1 divided by S plus B, and we'll look at step input and see what our steady state error is. So the error is like so. I've just substituted H, D, and G. Steady state error is given by limit as S tends to 0 S E of S, which is this expression here. I'm going to substitute R equal to 1 by S. This S cancels with this S. And then you set all these S's to 0. And what you get is this becomes 1 by A, this becomes 1 by B, this becomes 1 by 0, which is infinity. 1 divided by infinity is 0. So you get steady state error equal to 0, therefore perfect tracking. Perfect tracking is obtained when the steady state error equal to 0. Let's try out another example where the controller is the same, the plant is the same, the sensor is the same, but I'm trying to look at tracking for a ramp input here. So capital R is 1 divided by S square. So everything remains the same. Now I substitute for R like so. So one of these S's gets cancelled with this S. and then I bring the remaining s inside here like so. So this s gets cancelled by this s, and when I set s equal to 0, this becomes a 0. This, and since this and this is cancelled, this is a 1. This becomes 1 by a, this becomes 1 divided by b. So it is 1 divided by ab, which is equal to ab. 1 divided by 1 divided by ab is ab. So the steady state error is ab. It is not equal to 0. So you don't have good tracking for a ramp input. Let's look at disturbance rejection. Disturbance rejection is the ability of the system to completely reject disturbance input. So essentially what you want to have is you want to have the steady state error with respect to the disturbance input to be 0. Now here is a sort of an example what it means to reject disturbances. So this is your reference signal, and this is your output here, what you get. And then you have the disturbance signal like that. There's a bump here somewhere at this time. Now if you have perfect disturbance rejection, then this squiggly thing here should never happen. But this has reasonably good disturbance rejection in the sense you don't see this completely in here. If it was bad disturbance rejection, then this would have gone way up like that. So this is reasonably good disturbance rejection. This is what you want. This is the output. That is what you get. Ideally, the output should perfectly follow the input, which is your reference signal. So we are doing disturbance rejection with respect to the disturbance at the actuator. So set all the other inputs equal to 0. This is what the reduced system looks like. Now we need to find a relationship between WA and E. And if you do brute force block diagram deduction, this is the input, this is the expression for error. And we do the same thing as before. I have my controller is 1 divided by s, my plant is 1 divided by s plus a, my sensor is 1 divided by s plus b, and I'm looking at a step disturbance input. Substitute all those things in there, and I get an expression for the error like so. This is my error expression. And if I find steady state error is limit as s tends to 0 of s e of s. If you do that, you'll find that this equal to 0, so we have perfect disturbance rejection. So why is that? Because this s is 0, then this whole thing drops out. You get this divided by 1, and this as limit s tends to 0 of s, this is 0. So 0 times some constant is 0. We can go and do the same thing that we did before, look at disturbance rejection for a ramp input. Once again do the substitution, and this is what my error Laplace transform looks like. This is the Laplace transform of my error. I find steady state error similarly is limit as s tends to 0 s e of s. I do that and I get steady state error is 1 divided by 1 plus ab. So what that means is the system doesn't reject disturbances from the actuator disturbance input perfectly. You always get a residual steady state error.